Okay, so let us start. So today we are going to start with a new topic called equilibrium of forces in 3 dimension. So this topic is a little difficult to understand down the line, but in today's conversation it is almost everything is whatever we have discussed in the previous classes. So that is related to coplanar forces, right? So we will start with the similar kind of analysis what we have done in case of coplanar forces, and then we will extend whatever the extra part that is going to be there, so as part of this discussion. Got it? So equilibrium of forces in 3D. So before understanding this topic, right, so we have to be aware of the vectors in 3D. So vectors in 3D, so a vector in 3 dimension, right, so it is as if like a vector in 2 dimension, but only thing is, so only thing is a little difference. So the difference is, so in case of 2D, so this is x-axis and this is y-axis, right? So this is x-axis and this is y-axis. And then suppose if I take one vector like this, and this vector, if you notice, it is making an angle of theta with respect to the x-axis. Then, so with this only one angle, you will be able to identify the direction of this particular vector, right? So this is the r vector. Now, if I ask you to find out the angle from y-axis to theta, y-axis to this r, then you can straight away say that this is pi by 2 minus theta. But this kind of simplicity is not there as part of 3D vectors. So the reason being, if there are 3 different vectors, so let us say this is x-axis and that is y-axis and this is z-axis. So the left bottom corner of the room, actually let us say, if you say that that is the origin of the 3D coordinate system, then try to identify a point which is the ceiling fan in the room, right? So if you draw a vector from the bottom left corner to the fan, straight away one vector, then to identify the exact direction of that particular vector, you need 3 different angles. So that is where the complexity comes, right? So here actually, in case of 2D vectors, you need a single angle. So this is a single angle to identify the direction. So this is in 2D vectors, right? So I think so. Vishal, you are asking for question number 10. Anyway, so I will discuss that in the next class, right? So let me complete this topic today. Okay, see, so this is a single vector. So this, in case of 2D, right, you need a single angle. But in case of 3D, the complexity goes thrice. Why? Because to identify this particular vector, what we are talking about, that is drawing from left bottom corner to the ceiling fan. So this line is making an angle with respect to x-axis, and an angle with respect to y-axis, and an angle with respect to the z-axis. So all the 3 different angles, and each angle is independent. So that is the complexity. So here actually this angle and this angle are interdependent because the sum of these two is anyway 90 degrees. But that kind of simplicity is not there in case of 3D vectors. So it is making an angle with respect to x-axis. That means if you draw a slant line like this, let us say this is x-axis, the angle between this slant line to the horizontal line, which is the base of this particular room, right? So that angle, so it is making an angle of alpha. That means if I say that this is x-axis and this is z-axis and this is y-axis, so this is a 3D coordinate system. If you want to identify a point which is nothing but the fan point and this is the origin, so this origin to this line, if you draw it, right, so this is making an angle of alpha with the x-axis and this is making an angle of beta with the y-axis and this is making an angle of gamma with the z-axis. So 3 different angles and each angle is independent. right? So each angle is independent. Hence, actually, whenever you are talking about a direction of a 3D vector, you have to tell three different angles. So those angles we call as the direction cosines. So these are cos alpha, cos beta, and cos gamma. Why we call as direction cosines? As, see this vector, if you project onto the x-axis, now here actually I will try to correlate here. So this vector, the component along the x-axis is the r cos theta, and the component along the y-axis is nothing but this vector, this is r sin theta. Now if I want to find out the similar kind of coordinates or similar kind of components in this particular case, now there is only one component that we are going to find out, that is this value is r cos alpha, because this is making an angle of alpha with respect to the x-axis, and this is called r cos alpha. But we don't worry about the r sin alpha because that is completely meaningless for us. So there is nothing like r sin alpha here, right? So because we are not going to use that. Why? Because see this is the projected component onto the x-axis. Now the same thing actually if you want to put it on the y-axis, right? So you need to think about the angle beta. There is nothing like pi minus alpha or pi by 2 minus alpha. So that's where the complexity. So that's why you are depending only on alpha and only on the horizontal component. No vertical component is going to be there as part of 3D vector analysis. So this is equal to r cos alpha, which is nothing but the x value. And the same vector if you project onto the y-axis, now this projection is going to be coming here, and this value is, this is r cos beta. So imagine, so this diagram may be a little confusing. So that's why actually imagine within the room where you are in. So draw a line from the bottommost point to the straightaway fan point, and then try to project like this on the x-axis where I am standing in, and then that is going to be the x component, which is nothing but r cos alpha, where r is the length of this particular vector. So this is r vector. Now the same vector if you project onto the y-axis like that, so that y-axis is making an angle of beta. So then actually the component, which is nothing but the again horizontal component, and that value is going to be r cos beta. It's not r sin alpha. Got it? So r cos beta is the projected component onto the y-axis, and the same ceiling fan actually is projected onto the z-axis, which is nothing but this vertical line. Then that value is going to be the r cos gamma. So that is, this component is going to be r cos gamma, and all the three vectors together will make this particular vector. So this way you can express this vector as r cos alpha into I plus r cos beta into j plus r cos gamma into k, where I, j, k are the unit vectors. Along x-axis, y-axis, and z-axis respectively. See this. Vishal, actually, did you get the clarity on that? The projections? See this. The projections are very simple. So you might be thinking of the angle between x-axis and the vector, right? So this is on the plane, there is no confusion. But if it is 3D, then so very high level of confusion is going to be there. Why? Because see this, the angle that is going to be measured is in space, not on the plane. That's where the problem. So that's why you try to imagine a straight line that is left bottom corner to the fan. Just try to imagine that. And then find the angle between the x-axis and this particular line. So when you are taking about the coordinate axis, right? So left bottom corner, if you take as the origin, then the intersection of this wall and the ground is taken as the x-axis, and the intersection of the vertical wall and the ground is taken as the y-axis. and the intersection of this wall and that wall together is taken as the z-axis. Now if you imagine that way, then actually this corner, that corner will form the three coordinate axes, that is x-axis, y-axis and z-axis. Now this fan point where it is joining a line from the origin to the fan, and that line actually is in the space. Now this space line is making an angle with respect to the x-axis, this is a slant angle. Got it? So that means, so this is actually, I will try to explain this way. See this. Now this line is like this. If this is like this, then actually the angle between this space line and this x-axis is making an angle of alpha, and this is making with respect to the y-axis an angle of beta, and this is making an angle of gamma with respect to the z-axis. So this is how actually these three angles are separated. So these angles are actually to a line which is going in the space, not on the any of the walls. Got it? Understood now? Understood or not? Yeah. So this way actually if you are able to make out this alpha, beta, gamma values, then actually the component of the projection, that is in this case actually, so this is the vector, right? So this vector, if you project onto the x-axis where this angle is directly made there, so this angle actually will directly give a r cos theta at this particular location, which is nothing but the horizontal component. Now this space line, so which is like this, now it is making a horizontal component along the x-axis is nothing but this projection point onto this particular x-axis, and this value is going to be r cos alpha. Now the same point if you project onto the y-axis, so this will make r cos beta, because this angle is beta and this angle is alpha, and this is angle gamma, and this gamma actually will give a projection component on the z-axis, which is nothing but r cos gamma. Got it? Now you people got the clarity why we arrived at this r cos alpha, r cos beta and r cos gamma. So once you got this understanding, this vector can be expressed as r cos alpha. So this is nothing but r vector, which is nothing but the position vector xi plus yj plus zk. So this is the position vector. So this is r vector. Now the x value is going to be r cos alpha, because r is this length. Now how can we say that r is nothing but, which is the magnitude of this particular vector, can represent the length of the line? See this. This is the position vector whose coordinates are x comma y comma z. Now I am saying that this position vector is equal to xi plus yj plus zk. Now can I write this way? I am straight away saying that xi plus yj plus zk will represent this particular point. Now for a vector to represent, so it has to satisfy the direction condition, at the same time the magnitude condition. Now the magnitude of this particular vector is going to be length of this particular vector, which is nothing but, so this value r magnitude is equal to x square plus y square plus z square under root. X square plus y square plus z square is nothing but the magnitude of this particular position vector, which has to represent the length of this particular line. Now try to imagine that the fan point, which is at a location of x comma y comma z. Now the length of the line from the left bottom corner to the fan, and that length actually it has to be equal to x square plus y square plus z square under root. Now if it has to be equated to x square plus y square plus z square, now try to justify that the location can be x comma y comma z. Got it? Okay, so you got the clarity on how we are dividing this vector. Now actually I am asking you one question, that is, so this value square root of x square plus y square plus z square has to represent the length of this particular line. Now how can you justify if the coordinates of the fan location in the room is x comma y comma z? So the line length, so whatever is drawn from the origin to that line is equal to square root of x square plus y square plus z square. Now let me explain that. See this, if I want to reach the fan location from the left bottom corner, now I have to start from there, come to this location for a duration of x, and then travel exactly opposite to me for a length of y, and then climb a height of z for a duration of z, right? Now this is x, this is y, and this is z. if you notice, all the three lines are perpendicular to each other. Now this is x-axis and this is y. So this is making an angle of 90 degrees here. And then y and z is again making 90 degrees there. Now if I have to go there in a diagonal way, that is from like this. So this location, let us say this is x-axis and this is y-axis. Now if I have to go to the xy plane location, x comma y, then I have to go like this and then I have to go like this. Now this value is x and this value is y. Now I have reached this particular point. Now the fan is located at a height of z like this. Now if it is located at a height of z like this, then I can calculate this length. This is nothing but square root of x square plus y square. And then from there actually I call this as, let us say, P. And then this is having a height of z to reach the fan location. Now P and z are making an angle of 90 degrees like this. At this location it is making 90 degrees like this. Now P and Z like this actually you can form. So this is P and this is Z. It is making 90 degrees like this. So this length is going to be P square plus Z square under root, where P is equal to square root of x square plus y square. Now if I combine these two, so this value is going to be, I call this as mod R is equal to P square plus Z square under root is equal to x square plus y square plus z square under root. So this is square root of x square plus y square plus z square, which is nothing but, see, if I draw a perpendicular like this and then from there actually to reach the fan location from here I have to travel like this. So which is nothing but the length of this space vector. So that length is nothing but the modulus of this particular vector. So hence you can express this vector R as xi plus yj plus zk, which is nothing but a space vector. Got it? So the position vector in case of 2D you will be expressing as xi plus yj. Now here it is xi plus yj plus zk. So one extra variable here z, but the complexity is thrice. Earlier actually two variables can be brought together into a single value, theta. So by theta is equal to tan inverse of y by x and the modulus is equal to square root of x square plus y square. But here the angles are three. So that is, one value is cos inverse of x by r, another value is cos inverse of y by r, another value is cos inverse of z by r, which we call as the direction cosine angles, right? So that's why actually this xi plus yj plus zk can be expressed as the projected component onto x-axis, onto y-axis, onto z-axis like this. Now the magnitude of this particular vectors, if you try to calculate it, this is mod r is equal to x square plus y square plus z square, and the same thing you can even calculate as r square cos square alpha plus r square cos square beta plus r square cos square gamma. Now this value is nothing but modulus r square. So this is r square, if you cancel on either sides, you left with cos square alpha plus cos square beta plus cos square gamma is equal to 1, which is a famous relation where alpha, beta, gamma are the directional cosines. Got it? Understood? Because this level of vectors understanding in 3D is very much needed for having calculations on 3D vectors with the application of equilibrium of forces. Got it? So you can note down this discussion. So if you have any questions on this, you can let me know now. So in the previous classes, right? So when we are talking about the moments of the force, right? We have calculated the moment of the force is nothing but m is equal to r cross f is nothing but the moment of the force. Where, let us say, there is one force that is acting at this particular point, and then this point actually is the point of application of the force, if I say. So then actually this location is nothing but the position vector is nothing but AR. So this is the position vector AR and the force vector is F here. So AR cross F, or if I call this as R then this is r cross f is nothing but the moment vector. Now here, very important understanding of this movement vector is the direction of this movement. So the direction of the movement is nothing but a perpendicular vector to both r and f. Now here, these two being the coplanar vectors, r is on this and f is like this. Now the resultant of this is nothing but, if you extend like this, then actually this is how actually you are treating. So this is how we are treating, we mean this is an anti-clockwise direction. So anti-clock is treated as this direction. What it essentially means for us. So this is going to represent not the force direction. It is going to be the vector which is perpendicular to both, which essentially means that the axis of rotation. That means about which this object is getting moved. That means if you draw a straight line coming out of the board, then around that line actually it will try to move because of this force which was acted at a location of r. So this vector actually will try to move, this particular force will try to move in an anti-clockwise direction. So whose axis of rotation is coming out of the board. Suppose actually if I say that this force is in a counter direction, let us say in the opposite direction, then actually, so this same point of application, but the force direction is opposite to it. Then actually, so this is the direction of the movement, which essentially means that this is clockwise. So if this force is trying to move in the anti-clockwise direction, this force will try to move in the clockwise direction. Now one moves in this direction, another moves in the opposite direction like this. So opposite direction like this. Now actually the axis of rotation for this one is coming out of the board. The axis of rotation for this one is coming inside the board or going inside the board. So one opposite to the other. So based on this directional sign, right? So you will be able to exactly calculate the movement direction, right? The resultant movement direction. Suppose if positive is dominating, then actually the resultant axis is coming out of the board. If negative is dominating, then actually the axis is going inside, which essentially means that it rotates in the clockwise direction. Now the complexity comes in case of 3D. So there is nothing like clockwise and anti-clockwise, because in case of 3D forces, if there is a block, let us say, I will give you this way. See this. This is one particular box, and on this box actually there is one force that is acting like this, and there is one force that is acting like this, there is one force that is acting like this, and there is one force that is acting like this. Now actually none of the forces are coplanar in this particular case. Now in which direction it will try to rotate? So there are two different concepts actually what we have discussed in case of equilibrium of body. So one is the equilibrium of body in the linear direction. That means there should not be any linear movement like this or like this or like this or like this in case of 3D. If it is a linear in 2D, then actually straight away it may go in this direction or it may go in this direction. This is the linear direction. Now the movement actually will try to rotate this particular body either in the clockwise direction or in the anti-clockwise direction. So these are the only two possibilities. But in case of 3D, what happens is this can rotate like this, or 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 this can rotate like this. So there are infinite number of possible ways so that are there for the rotation of this particular body. Now for the equilibrium of the 3D case, right? So you have to assure that all the infinite different directions actually there shouldn't be any rotational force. So then only we say that the body is under equilibrium condition. Now that one actually we are going to deal in a systematic way. So this one actually the rotation, right? So there are actually infinite number of possible rotationals possible. But in case of coplanar vectors, there is only two different possibilities, either clockwise or anti-clockwise. But in case of 3D, so there is nothing like clockwise and anti-clockwise. It can rotate in any direction. All the 3D possibilities are there, right? So in such cases actually how we are going to deal with. So that's what is our discussion in case of equilibrium of forces in 3D. So linear is actually, but mathematically more or less actually exactly what we have done in the previous classes, actually we are going to deal exactly in the similar manner, but two quantities extra actually we are going to come. So we are going to get in. So for the equilibrium of body in 3D, so So we have to assure that the resultant force has to be equal to 0 and the resultant moment has to be equal to 0. So the fundamental conditions are exactly same. Now the methodology is a little bit different. So the fundamental conditions for r equal to 0 is again what we have done in the previous classes. That is, if you divide this particular vector r into xi plus yj plus zk, so then actually for the linear equilibrium of the body, we have to assure that the x has to be equal to 0 and y have to be equal to 0 and z has to be equal to 0. So this is the basic necessary condition for the linear equilibrium of the body. So x equal to 0, y equal to 0 and z is equal to 0, where x, y, z are the algebraic sum of all the force components that were resolved into x-axis, y-axis and z-axis. So these are the resolved component of the forces along x-axis. That means if there are multiple forces that are there, so each force has to be divided into 3 different components along x-axis, along y-axis and along z-axis. Now if you want to divide the vectors into x-axis and y-axis and z-axis, so you have to be thinking about the direction cosines angles, that is alpha, beta, gamma values actually we have to be identifying it. Now how we are identifying this alpha, beta, gamma is based on the previous relation, that is, so r vector can be expressed as xi plus yj plus zk. Now the same thing actually we can even express as r cos alpha plus r cos beta into I into j, r cos gamma into k, right? So this is the r vector. Now this r is nothing but the modulus of this particular vector. If I take common and then actually can bring this one, now r bar by r, so this value is equal to cos alpha into I plus cos beta into j plus cos gamma into k. So this is nothing but the unit vector. So this is r cap, right? So if you take this particular vector, so r cap, then this cos alpha, cos beta, cos gamma can be expressed as, so this is x is equal to r cos alpha and cos alpha equal to x by r and cos beta equal to y by r and cos gamma is equal to z by r. So these are the direction cosines. So alpha, beta, gamma will give in which direction that particular vector is dealing with, or in which direction that particular vector is having force effect on it, right? So this is x by r and y by r and z by r are the four, so directional cosines which will give the direction. Now there is a difference between directional cosines and directional ratios. So directional cosines means, so cos alpha, cos beta, cos gamma, these values actually will try to give the direction, but it won't talk about the position. That means suppose if I take this particular chalk piece, this is having a direction like this. Now the same chalk piece is moved to like this. Again the direction is same but the location is different, right? So this one, whatever the direction, right? So it talks about that is going to be dealt with the help of alpha, beta, gammas. So alpha, beta, gamma will give the direction, but the directional ratios is nothing but the position where on the x-axis, where on the y-axis and where on the z-axis. Got it? So that's why when we are dealing with these vectors, right, you have to be aware of what is directional cosine and what is directional ratios. The x location, y location, z locations are nothing but the directional ratios. Directional cosines we mean the angle in which the particular force is acting with respect to x-axis, with respect to y-axis and with respect to z-axis. Now here these values, x is nothing but the horizontal or the x component, y is nothing but the y component, z is nothing but the z component of this particular position vector. Now exactly in the similar manner, if a force is expressed as fx into I plus fy into j plus fz into k. So if this is how actually a force is expressed, which essentially means that this fx is the force component in the direction of x and this fy is the force component in the direction of y and fz is the force component in the direction of z. Now let us say this is f1. So this is fx1, fy1 and fz1. Similarly, if I have one more force, f2 is equal to fx2 into I plus fy2 into j plus fz2 into k. So this is another force component or another force which is acting in the direction of F2, which is nothing but fx2 into I, fy2 into I, j plus fz2 into k. Now, if you want to find out the resultant force components that are acting in all the three different directions are nothing but the algebraic sum of these two. That is, along the x direction, this is f of x1 plus fx2, and along y direction, fy1 plus fy2, and along z axis, this is fz1 plus fz2. So these are the force components or the effect of all the forces together along x-axis, together along y-axis, and together along z-axis. So if all the forces together are equal, that means if this x equal to 0 and this y equal to 0 and if this z equal to 0, then we say that so the body is under equilibrium condition linearly. Got it? So this is how actually you will be assuring the linear equilibrium of the body. So there is no procedural difference between coplanar forces and 3D forces in case of linear movement. But a little bit of difference is going to be there definitely in case of calculation of the movements. So you can note down this. Now some of the theorems are the basic theorems what we have used in case of coplanar forces. Same is applicable even here also. That is, if a random force is acting on a body, let us say there is a force that is acting on this body at this particular location, then on the coordinate axis, this is x-axis and this is y-axis and this is z-axis, or this is z-axis and this is y-axis. Now if you draw this, then actually, so this is the force actually that is acting on this particular body like this. So this is I call as F, and the same force can be interpreted as if like there is one force that is acting at a randomly chosen point O here along with a couple. So that is one basic theorem what we have learned earlier. So exact procedure what we have adapted there is try to draw the same force, that is this force actually I can draw exactly parallel and magnitude wise equal. So this is F, and then in the opposite direction also from the randomly chosen point of O you try to draw the same force so that these two will cancel out. That means you have applied a zero force at origin for all practical purpose because you applied the opposite forces here. Now this force which is acting in the negative direction together with this particular force, so this is going to form a couple. This is going to form a couple. Now if these two are forming a couple, there is one particular force left over. So this is the leftover force. Then based on this understanding, we can straight away state that every force which is acting on a body can be resolved into one couple whose magnitude is equal to R cross F and a resultant force which is acting at a randomly chosen point of O. So this is a randomly chosen point. So this is based on the coordinates x actually what you have selected for. So if you assume this as the origin, then you can draw x-axis, y-axis and z-axis, and then you can straight away draw one force opposite direction to the other one. Then actually there will be a couple and there will be a resultant force which is acting on the newly selected origin at this particular location, right? That means you have got the flexibility wherever you wanted to select the origin, you can still select it, and then this particular force can be interpreted as a movement plus a single force acting at that particular point. Now if there are infinite number of forces or actually there are multiple forces that are acting, then each force can be done in this particular manner even though it is 3D forces, right? So the same thing what we have done in case of 2D. So in case of coplanar forces we have exactly done the same thing, but only difference is the force can be now in this direction on a plane, or it can even a force which is acting like this particular chalk piece where this force is acting from out of the board into the board, and there might be other forces from inside the board also. There might be forces from the top also, bottom, left, everything, but every force can be interpreted in this particular manner. That means, so if I have actually 4 different forces, then actually at the randomly chosen point of O, So I can imagine all the forces acting like this. Like this. So this is F1 and this is F2 and this is F3 and this is F4 and this is F5. If there are 5 different forces, I can imagine that though all the forces are acting at different points of applications of this particular body, all the forces together I can interpret as if like all the forces are acting like this. Now once I came to this particular conclusion, then actually I can divide this particular force into the horizontal component and the vertical component, or in case of 3D, the X component, Y component and Z component. So every force can be divided into different components, X component, Y component and Z component. Now if I divide all these forces into X component and Y component and Z component, then I can easily sum up in the positive X direction as the plus and in the negative X direction as the minus. So you can sum up all these things together so that if it is coming out to be 0, you can say that in the X direction there is no linear movement, hence it is under equilibrium condition in the X direction. Similarly, if you sum up all the Y component of the forces to 0, then you can say that so there is no linear movement in the direction of Y, hence it is under equilibrium condition in the direction of Y. Similarly for the Z direction. That means if all the 3 different directions, if you are assuring that X, Y, Z, so where X is equal to Fx1 plus Fx2 plus Fx3 plus Fx4 plus Fx5 is coming out to be 0. So this is under equilibrium condition. Similarly for Y, similarly for Z. Now all the 3 equations together, so you can say that, so this is 0. Then actually you can say that the body is under linearly equilibrium condition. Now based on this understanding, now we have got actually whatever may be the number of forces, each force contributes to a moment as well. So that moment actually we have to be calculating. Now this is a 3D moment. That means there is nothing like clockwise and anti-clockwise. But for a single force, if you can think of, so you can consider in the positive direction and negative direction for that particular one. Now here, whenever we calculate the moment is nothing but if you draw a position vector like this, then I call this as R1 and this force as F1 and the moment is nothing but M1. So M1 is equal to R1 cross F1 is nothing but the moment. Now here actually, when we are dealing with multiple forces which are not coplanar, so we don't say either clockwise or anti-clockwise direction. So there is a resultant vector which is acting perpendicular to both these particular vectors, R1 and F1. So that direction may be any direction. So it will also have a definite directional cosines. But it's not like clockwise and anti-clockwise. It is like R1 cross F1, whatever may be the direction it is going to come in, that direction is nothing but the moment direction. Now, if there are multiple forces that are acting, now each and every one will have a different direction. And obviously, the sum of all the forces together or the sum of all the movements together, so it will try to result into a single direction, which is nothing but, so M is equal to Li plus Mj plus Nk, where L is the direction cosine of the movement in the direction of I, and this is the direction cosine of the movement in the direction of J, and this is the direction cosine in the direction of K. That means here actually it is not a point now, so it is going to be an axis. That means this particular body, when it is rotating, right, so it might rotate like this or it might rotate like this. So that means this axis, so if I draw a parallel line like this, then it can rotate like this. If I draw a vertical line like this, it might rotate like this, and opposite direction also. Even for the x-axis also, it might rotate in this direction or it might rotate in the opposite direction. For the z-axis, it might rotate in this direction or it might rotate in the opposite direction. Now, if I take y-axis, that is, if I take this particular chalk piece as one axis, then it can rotate like this or it can rotate in the opposite direction. Now actually, all the 3 different directions and exactly opposite directions together will be resulting in this particular format, that is Li plus Mj plus Nk. Now these values actually will give an axis which is nothing but somewhere based on this Lm n values. So this line may be like this, where my finger is there, right? So my finger actually, it is just drawing a line like this. Now this line actually is the resultant direction, then which essentially means that this body will try to rotate about this particular axis like this. Got it or not? Understood? Any questions on this understanding? Try to imagine that, the 3D space. So this particular 3D body actually, it can rotate in all the 360 direction in any plane, whatever you can think of. That means, try to imagine the ball. So if I ask a simple question, in which direction the ball can spin? So what is the answer for that? In which direction the ball can spin? Yeah, so the answer is infinite. So any number of ways actually it can spin, right? So any number of direction, but every direction will have a different directional cosines. So that directional cosines is going to be dealt with this particular one. This m is nothing but the sum of all the moments together. That means if I have 5 different forces, then actually, so G is nothing but, so R1 cross F1 plus R2 cross F2 plus R3 cross F3 plus R4 cross F4 plus R5 cross F5. Now the sum of all these things will definitely will have a single vector. So that single vector is nothing but, so Li plus Mj plus Nk. So this is the moment G. And this will have definitely one associated direction about which this particular body will try to rotate based on this particular direction. Got it? So now actually the next level of understanding is, if I wanted to make the body has to be under equilibrium condition, so individually L has to be equal to 0, M has to be equal to 0 and N has to be equal to 0. So that I can say that the body is under equilibrium condition. Now here L is nothing but the resulting movement of the body for the rotation about the x-axis. That means about the x-axis we mean, if I draw a line parallel to the x-axis, then actually, so all the forces together can rotate in this particular direction, that is about OX direction. So this is nothing but the direction which is parallel to the x-axis. Now this direction is nothing but the parallel to the y-axis, and this is parallel to the z-axis. Now here this L, M, N are nothing but the resulting movements in the direction of x, in the direction of y, and in the direction of z. Earlier actually we were talking about a point of application for calculation of the moment. Now actually it is going to be an axis of moment. Earlier also it was axis only, but actually we have identified the location from where it is passing through. Anyway, we know that it is perpendicular to the plane. But here actually we are not sure that, or there is no defined plane of perpendicular here. Hence actually we will be talking about the straight line rather than a point. Got it or not? So earlier actually, being always, in case of 2D, R cross F will always be perpendicular to the plane. Then actually, if I say the point from where this particular axis is passing through, then that is sufficient enough. That's why actually we were taking the moments about a point. So that is how actually the statements were made earlier. But there also, it is nothing but the moments of the force about a straight line which is passing through that point. Now here actually we are making explicit. Why? Because there is no defined plane in this particular case. Got it or not? So all these movements are nothing but L, M, N are about x-axis, about y-axis and about z-axis. About we mean, it's not that this body is trying to rotate about x-axis like this. It is rotating with an axis which is parallel to the x-axis. And this is rotating with a parallel axis which is passing through this particular point. So that is like this. And it may be in the z direction like this. So in any direction actually it can rotate. That's why there is no defined plane. Hence we have to be talking about L, M, N, which are nothing but OX, OY and OZ. Got it? Any questions on this? Any questions? Okay, yeah. So I'd like to stop the class for today. So you can note down this. In case if you have any questions, you can let me know now. Any questions? Okay, yeah. So that's all for today. Yeah, thank you. Yeah, good night.